Okay, so this is definitely not how I'd like to do this, but your test is going to be during your next class. Obviously, I'm not here today, so I'm going to try to give you everything that's going to be on the test, including going over some of the problems that we had in the two problem sheets. So things that you need to know for the test, for one thing, this is chapter 6. We titled it Momentum Impulse Collisions. So we want to know the equation F equals, Ft equals change in P. All right, from here we should know that that's force, change in time, and our change in momentum. Our change in momentum equation is M change in V. If we wanted to expand that, we could do VF minus VI. Okay? Some students like to see it that way. Some students like to see it that way. We also defined Ft as the impulse. And I said be careful on questions on the test, because if they're multiple choice questions and they ask you what is the impulse, this is what you're going to answer. In the problems, however, though, if it mentions something about the change in momentum, you need to know that that's also equal to the impulse. Okay. Sometimes the units for impulse are written as Newton times a second, but they could also be kilograms, meters per second, which is the same exact thing. So that's a very important equation. It is really, when it comes down to it, those are really like the two equations that you need to know. You also need to have an idea of graphing F and T. And in class when we did the graphing, or at least we talked about it, I know some of you are probably laughing because of me using this computer. There we go. But we had some simple graphs drawn like this, where what we'd be trying to find is the area under the curve, or under the graph, however you want to look at it or say it. So what we tend to have are pretty constant forces, and if they do change, maybe they look something like that. And the way we can solve that is we can section it off and find the area for the square, find the area for the triangle, and maybe find the other area for that rectangle. Obviously, I guess we could have found that all together at once and then added it up to the triangle. So that's how we're going to do it. We're going to stick to basic measurements, for example, length times width, and that's how we'll solve the impulse, okay, for the graphs and the collisions. When we have different types of collisions, okay, and different types meaning elastic or inelastic, the graphs might look a little bit differently. So it'd be good to know the difference between something like this and something like this. Like maybe an example for each. This could be knees stiff, this could be knees bent. If that were the case, as far as the one class goes, and it's your class, we know that the impulse underneath would be the same. Okay, the area under each graph would be the same, even though it doesn't look like it here. And the change in momentum is actually the same, but we increase the time but decrease the force. Okay, that's what we have here, an increase in time but a decrease in force. So anyway, to finish that up, we just need to have an idea of what each one would be, an example of each, if I give you some different graphs. So let's go to collision types. I mentioned that we have elastic. On top of that, we can call it perfectly. Right? Perfectly elastic. We have elastic. We have inelastic. And then we have perfectly inelastic. If you remember in class, I said most collisions fall between those two. Okay? And the reason that is when we have an object that is deforming, we have an object that's deforming and coming back. We call those inelastic. And a good example of an elastic collision would be like a couple metal balls hitting each other, or billiard balls. Okay, and so most of our collisions fall somewhere between something being really deformed and then not being deformed much at all. So that's why we say that. For all of these, when we talk about what is conserved, in the elastic collision we have the kinetic energy, and we also have the momentum. I was going to write potential energy there for a second. So the kinetic energy and the momentum. Same thing for elastic, because it's a type of elastic collision. So we have kinetic energy and momentum. And then for inelastic, we only have the momentum being conserved. The question could come up, well, where did kinetic energy go? Or why don't you have all of it being conserved? And the reason is when it deforms, it loses that kinetic energy to thermal. Okay, some of it. I'm not saying all of it, but some of it. Right. So what does it mean? What does it mean to have kinetic energy conserved? Well, we have KE of the first object initially plus KE of the second object initially, equaling the kinetic energy of the first final plus the kinetic energy of the second final. We could then plug in, and I'm not going to do this, but remember that KE is equal to 1/2 mv squared. What I'm seeing a lot of is people forgetting that square. Okay. Now remember, this is only for elastic collisions. My recommendation is when it comes down to doing this and using it, we don't. Every chance that we get to use the conservation of momentum, we should do that. So let's write down the conservation of momentum now. It'd be P1I if we have two objects, which we always do, and we have P2I. That would equal P1F plus P2F. If we write that out further with momentum equaling mass times velocity, we would get mass 1 V1I plus mass 2 V2I equaling mass 1 V1F plus mass 2 V2F. Now the tough part, I think, is remembering where everything goes. Okay, so most of the time it would be good to draw a picture. It'd be nice if it just didn't keep popping up on me. You all know how to get rid of that, but obviously I don't. There you go. All right. So it's also nice if one of our velocities is 0, either at the beginning or at the end. So if we have mass 1 coming into mass 2, and mass 2 isn't moving, well then we have the initial velocity being 0. And then we can just get rid of that part. And that's really nice to have that happen, because it just makes the problem look a little easier. So most of the time when we have these problems, what we'll be given is everything except one velocity, or maybe a mass. Either the velocity or the mass, but we're only going to have one of these unknowns. Sometimes when you look at problems online and whatnot, they give you two unknowns. We're going to stick to one unknown for now. Okay. So this equation right here, you could use for all types of collisions: elastic, inelastic. If they hit and stick perfectly inelastic, it doesn't really matter. So now that they came up, let's go back here for a second and let's talk about this one. This is the special one, because it's the only one out of all these that if you have two objects, they hit and they stick, which means that the final velocity is the same for both. And so the right side of that equation will end up being m1 plus m2, and that makes sense to add up the masses because they're stuck together now, times the final velocity. And once again, if they hit and they stick and they move together, then they should have the same final velocity. So this part down here, just for perfectly, if v and v are the same and we can factor them out, that would make that, I think, a little bit easier. And that's really basically when it comes down to what's on the test. Okay, there's not a lot of like defining. You need to know impulse. You need to know what momentum is. Impulse momentum theorem, which is just this equation. Okay, that's just that equation, the impulse momentum theorem. And that's about it. Everything else you've already had. Grab that over there. One thing that pops up here, and I notice now that I forgot, is signs are very, very important. I know in the last chapter when we were doing potential energy and kinetic energy, we sometimes ignored some signs as far as the gravity goes and that sort of thing. Here, very, very important. If we have mass 1 and mass 2, and this one's colliding, and let's say mass 2 goes that way at the end, well, what's mass 1 doing? The sign will help us, okay? If it doesn't tell you what mass 1 is doing and it asks, well, what's the final velocity of mass 1? Mass 1, it could either be going forward, if you think about it, or it could be going backward. Think about a basketball hitting like maybe a bowling ball. If the basketball is going forward, it probably hit the bowling ball and bounce back, okay? But some things, it's dependent upon that. All right, so be careful with the signs, make sure that you use them, and please, please watch the algebra and not believing that the calculator knows more than you, okay? You have to remember when you do these equations that you do whatever on top and then divide by the whole bottom, okay? What we're finding is, what I'm seeing still with the calculations is, we punch it all into the calculator once and we tend to mess that up a little bit, all right? So we're gonna take a break and then get into the homework problems. Our first problem sheet was called Momentum and Impulse, and it consisted of 3 problems. The same thing with the other one, but this one had 3 problems. It says a ball striking a wall, and it gives you some values here. Okay, if we notice, it says the change in momentum is 3. It has a time interval, which is the change in t over here, of less than 0.2 seconds. And we want to know what is the average force applied to the ball, and we also want to know what is the impulse of the collision. So it might look a little bit more difficult than it is. But the point of all of this is to recognize something. I lost all the notes I just did. That's okay. So, first off, we're going to do the impulse equation. Okay. So we have F, change in t, equals the change in p. The one thing it gives us is it says the change in momentum is 3.00 kilograms meters per second square. Just meters per second. And then A asks us for what is the impulse. Well, we know that this is the impulse, but we also know that it's equal to the change in momentum. So that is really easy. Okay, you don't really need to rewrite this. If you were to write it like this, I would understand that you would understand what you were doing. And saying that the momentum is the same thing as the impulse. The second part is B, where it says, what is the average force? Don't let words like average throw you off, okay? When we're solving for the average force, it means we're just solving for the force. So we're going to divide each side by t, right? And that will give us F equals P over T. And that is 3.00 kilograms meters per second divided by 0.189 seconds, I think, if I remember correctly. One thing I forgot to mention here, it is a plus. If they don't mention it, then we know it's a plus and it's a vector, so we need that, okay? And when you do this, divide out, you get 15.9 newtons, okay? If we look at the significant figures, we have 3, and we also have a plus sign on the F, okay? That's probably pretty close to being the simplest problem that would be on the test, besides just saying what's P, and you gotta multiply M times V, all right? So, but the things to realize is this equals this, so we can make this, okay, determination. And then when we're solving for average force, we need to make sure we have the positive sign and that we have 3 significant figures because 3.00 is 3 and 0.189 seconds is also 3 significant figures. So